plus Cl dot. When I sum those steps together, blah, 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 we get CHCl3 plus chlorine gives rise to CCl4 plus HCl. So all of these are propagation steps. I consume one free radical when I generate another. And that allows the chain to live, to propagate. Consume one, make another, the chain lives. It's a propagation step. And so there's initiation, which makes the original free radicals, which begin the process. The process is continued, the process propagates by one free radical attacking an intact molecule, generating another free radical, and on and on and on it goes. But the point I'll make is that imagine we started this with a couple hundred chlorine molecules fractured. Let's say it's 100 fractured. They'll give 200 Cl dots in a morass of methane molecules and chlorine molecules. But if you look at the sequence, if you look at the cascade of reactions, of those 200 Cl dots that we made, one goes in, one comes out, and I make monochloromethane. So there's been no net destruction of the Cl dot, right? I made it at the end of the sequence. Let's imagine that one comes in, and another one comes out. And I've now turned the wheel and made dichloromethane. That one goes in, another one comes out, and I've made trichloromethane. Now, I'm consuming Cl2s, right? So the wheel can't turn with just Cl dot. I need the Cl2s. But for every time I do a substitution, I make a new Cl dot. And that Cl dot starts another pair of reactions that turns the wheel and makes the trichloro and the tetrachloro. So I don't need, nor do I want, all the chlorines to fracture at the beginning. I don't. Because one Cl dot could parent the wheel turning to make chloromethane, dichloromethane, trichloromethane, tetrachloromethane, and then still start another set. So when you don't want the breakage, the homolysis of the chlorines to be 100% efficient, you don't want to be anywhere near that number. 2 or 3, 4, 5% efficiency is more than enough, because the Cl dots are what keep the chain turning. And you need the Cl2s to be the fuel for the process. Okay? So the Cl dots are like the levers, and the chlorines are the fuel for the process. Okay. Eventually, what happens as you start going through rotation after rotation, you're making compound after compound after compound, is that the population of free radicals goes up. And after some time, you're going to start, one free radical is going to start to encounter another. Who will encounter whom? It's a crapshoot. It's entirely random. So you could get a CH3 dot collapsing into a Cl dot, and that gives you CH3Cl. Or you can get this collapsing into a CH2Cl dot, and you get CH2Cl, or it can collapse into a CCl3 dot. And you can get CH3CCl3. So you can get a whole number of different products. And it's all random. These steps really are the opposites of initiation. Because initiation took an intact molecule and made 2 free radicals. In this, you are consuming 2 free radicals, and you're making an intact molecule. These kill the reaction, because the reaction requires free radicals to turn the wheel. If I consume them, I will stop the wheel from turning. So these are called termination steps. So terminations are the opposite of initiations or initiation, because I consume two free radicals to make an intact molecule. All right, so the bottom line here is that if I were to do this reaction, I will end up with a range of products. Mono, dichloromethane, trichloromethane, tetrachloromethane, and so on, as well as HCl. And to boot, a bunch of products that were formed by random collision of random free radicals. So I say all this to say that in the classic way of doing free radical halogenation, it is complicated by the randomness. And so what you end up with is just a morass of products. So from a synthetic perspective, it is a weird path to take, because you lack control. I'm going to make 2 quick points here before we move on. For a couple minutes. And the 2 points I'll make are that if, for example, you were in charge of a lab and the lab says, I want to make dichloromethane. How would you make it? Let's say we're doing free radical chemistry, which is the ideal thing of doing. Well, what you would not do is start with methane and press along until the concentration of monochloromethane rose, and then you've got Cl dots attacking monochloromethane and dichloromethane. If you do that, you'll end up with a mixture of dichloromethane and monochloromethane. Plus, you're going to start to get the other products as well. What most people would do is start with the monochloromethane. Start here. So there's no problem with methane. Start with monochloromethane and carry out the reaction until you get dichloromethane. How will you prevent it? Well, I erased it. But how would you prevent the dichloromethane from getting further attacked by Cl dot? And if you think it through, the only time that will happen is when the dichloromethane concentration rises to a level where it begins to compete against monochloromethane. So you don't let that happen. In other words, I'm going to start off with 1 trillion molecules of this, and maybe 1 billion molecules of those. So the concentration of this is always so much higher than the concentration of that. So that the concentration of dichloromethane never rises to the level where it threatens monochloromethane. So the only thing the Cl dot will see to attack is this. And you can carry out the reaction by a constant process where you're feeding the system monochloromethane. That way its concentration never ever falls to the point where this can begin to compete against it, or God forbid, out-compete it. Okay? And then the last point I'll make on this is that if I look, and I won't go into the details, but if I look at this compound, and so alkanes, as we said, are relatively inert compounds. They burn, everybody burns, it's CNH. But then the only other reaction of importance that they undergo is free radical halogenation. If I treat this compound with halogen and light, so X2 is the halogen. Again, in this case, X is either chlorine or bromine. Fluorine is entirely too reactive and misbehaves badly. Iodine is entirely too unreactive, and you don't get much chemistry at all. So for this particular set of reactions, we're only interested in chlorine and bromine. Now, if you do this reaction, you're going to end up with 4 products. Well, yeah. You'd end up with 4 constitutional isomers. So I'll get products where I've got X on this carbon, product where I have X on that carbon, products where I have X on this carbon, and products where I have X on this carbon. So I'm going to get 4 constitutional isomers. We will see in short measure that there are actually 2 of these, but that's another question. When X is equal to bromine, when X is equal to bromine, what I will get is something that resembles the following distribution. I'll get 25% of this, I'll get about 17% of this. I'll get about 33% of this. No. Let's see. So we get 50% of this. 17. And then I'll get what, let's call this 8% of this. Yeah, okay. So if you look at it, in all, I have 3 H's here, 2 H's here, 1 H here, and then these are equivalent. These are equivalent, and that's 6 H's. So 6, 7, 9, 12. So statistically, what I should get is 3 over 12. In other words, that's 25% of my product here. And since it's twice that number, I should get 50% of my product on those metals. I've got 2 of the 12, so that's 1 over 6, which is about 17%. And then I've got 1 of 12, which is about half of that, that's about 8%. So what I would expect to see, and which is roughly what I see, is a statistical distribution of my products based upon the number of H's, number of available H's at each side. So when bromine reacts, it reacts statistically. And again, this is just a question of random collisions. The Briard dot is twice as likely to bump into these than they are to bump into those, because there's 6 of these and 3 of those. So I would get statistically twice as many of these as I do those. But there are 6 times as many of these as I have that one. So I'd expect the yield of the product from here to be 6 times the yield of the product from there. And that's what I see. That's roughly 6 times 8 is about 48. So roughly I'd expect to see 6 times as much of this one as that. So when bromine reacts statistically. Great. So what does that mean for us? Well, what it means is that because you tend to have more primary H's, right, than secondary H's, than tertiary H's, statistically what this means is that for bromine, we get preference with primary over secondary over tertiary. So if your intent is to functionalize a primary position in the molecule, use bromine. Because statistically, bromine targets the more abundant primary H's. But when X, okay, this is for chlorine, not bromine. So all of that I just said is for chlorine. And by the way, the reason that it's for chlorine is that chlorine is a more reactive halogen. And the more reactive things tend to be less discriminant. So if all you've missed today is breakfast, and you've got, day-old bread, and you've got, steak, whatever. Well, if all you've missed is breakfast, it's not that bad. You kind of leave the day-old bread and you go after the steak, right? But if you've missed breakfast, lunch, and dinner, and then the next breakfast, and the first thing you're seeing is day-old bread, you're probably going to go after the day-old bread. So the hungrier you are, the less selective you are, the less picky you are. So chlorine is very hungry and tends to be less picky. In other words, it tends to behave statistically. But when X is equal to bromine, the bromine tends to react in more, because it's less reactive, it takes its time, samples different sites, and tends to react based upon which site is better. So which site is better? If you remember, when we talked about them, free radicals are electron poor. The carbon does not have an octet. So anything that dumps electrons into this carbon will stabilize it. What dumps electrons? Alkyl groups. So what this means then is a tertiary radical, which has 3 R groups dumping electrons onto the carbon, is more stable than a secondary free radical, which only has 2 R groups stabilizing the free electron. That's better than a primary free radical, which only has 1 R group, but of course that would be better than the methyl radical. So free radicals and carbocations, and for that matter alkenes, we see that later on, are kindred in that the more R groups I have attached to them, the more I stabilize them, because they're all electron poor. So really, the best site on the molecule to attack, not the most abundant, but the best site, is tertiary, followed by secondary, followed by primaries. So if I were to do the reaction with bromine, which is more selective than chlorine, the bromine would probably give me something like maybe 30% of the product where the carbon, where the halogen goes in the tertiary site. And then I'll probably get, I don't know, maybe 20% of where it goes in the secondary. And then the rest of it, so I have, what am I using? So 50, so I'm going to divide that by 3, which is 16. So I'll probably get about 32% of this one, 33%, and maybe 17%. Right? So what I'll see is, again, because I have twice as much of these and I have that one, that's probably what I'll see here. But you'll notice that I've got an enhancement in the yield of the tertiary product. So if my intent is to functionalize a tertiary site, then I'm going to use bromine. So bromine is going to favor tertiary over secondary over primary. So you have some control over the randomness of the reaction. And again, if you look at this, you'll say, well, geez, I still get more of the primary than the tertiary. And that might be true. But you have, this primary has a six-fold advantage in terms of the number of H's. And yet the amount of the product here is almost competitive, right? Which indicates how much this side is favored in the reaction. So again, the different halogens, chlorine and bromine, target different sites in the molecule. If my intent is to functionalize the primary site, then I will go after chlorine. If my intent is to functionalize a tertiary site, I would use bromine as my reagent. Okay. So let me just put the question here really fast, just as an illustration. Suppose I asked you to convert this compound into that compound. Okay. What happened? Well, I have an H here, which I've converted into a T. How do I do that? Well, you know, one of the ways of bringing in a T, a single T, is to make this compound from the corresponding bromochloro compound, say Cl. Because I could do that either with zinc and T3O+, that's a direct reduction, or I could convert that into the alkyl lithium and treat it with T2O. Well, how do I get this? What I've done is I've functionalized the tertiary carbon. So I'm going to use bromine. So bromine in light, and then I'm going to separate. And all separation means that you don't have to tell me how you separate, just if you recognize the need to separate. Because I'm separating because in addition to the bromine going here, I'll get some of the bromine here, 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 and here. So this is an acknowledgement you're going to get multiple products. You don't want them all, you just want this one. Oh shoot. So this would be CF, this would be BR. Okay? So that's the kind of question you would see. Or I could say, if I look at this, chemistry is happening at the tertiary site. To do chemistry at the tertiary site, I need to activate the tertiary site, which means using bromine in light. Bromine with light. Okay? Okay. So let's stop there. We'll pick up from here next day.